let's start our discussion on CMOS amplifiers. So again, let us describe the equations or models pertaining to the MOS transistor. So let's have here the transistor current and voltages. So for MOS transistor, the output current is the drain current ID. And again, drain current would be the same with the source current. So since the current will pass through drain region and then through the internal channel and go out of the source region. So drain current and source current are equal or the same in MOS transistor. And as for the gate current of MOS transistor, gate current is considered to be zero because of the insulating oxide layer. So ID equals IS, while IG will be set to zero. Now for the voltages, you have the drain voltage. It is the voltage from drain to ground. Gate voltage measured from gate to ground. And source voltage measured from source to ground. Then the voltage between the gate and source, that is VGS or the gate source voltage. Then voltage between drain and source is denoted as VDS or drain source voltage. Then for the parameters of MOS transistor, we have VTO, gamma, P, Kp, and lambda. VTO is the threshold voltage when VSB or the source to body voltage equals to 0. Gamma is the body effect parameter. P is the potential during surface potential during strong inversion. Kp is the transconductance parameter. Then lambda is the channel length modulation parameter. So these parameters are normally provided to describe a MOS transistor. Then for the threshold voltage, we can use this model or equation. So threshold voltage VTH equals VTO. This is the threshold voltage when VSB is equal to 0, plus gamma, the body effect parameter, multiplied by the quantity of square root of P, the surface potential at strong inversion, plus the absolute value of the source to bulk voltage minus the square root of P. So we can use this equation to determine the VTH. So this will be needed if BSB is not equal to 0. If BSB is 0, then VTH will be equal to the VTO. Now for the cutoff condition, this happens when the gate source voltage is less than or equal to the threshold voltage. So in this case, the drain current will be set to 0. And then under the linear or triode operation, the gate source voltage is greater than the threshold voltage. And the drain source voltage is less than compared to the difference of the saturation voltage, which is the VGS minus VTH. So if these two conditions are true, we are going to use this equation or model. So ID equals Kp, the value over L, all multiplied by VGS minus VTH, or multiplied by VDS minus 1/2 VDS squared. And then the MOS transistor is operating in the saturation when VGS is greater than the threshold voltage and the VDS is greater or equal to the saturation voltage which is VGS minus the threshold voltage. And again, if these two conditions are true, we are going to use this equation or model. So saturation current ID equals 1/2 Kp W over L multiplied by VGS minus VTH squared multiplied by the quantity of 1 plus channel length modulation parameter lambda multiplied by the drain source voltage. Again, the VGS minus VTH, that is the VDS at the saturation point. And for the amplifier application, we want the MOS transistor to be operated in the saturation condition. All right, please confirm if you can see the whiteboard.
Yung PowerPoint pa po yung nakikita, sir.
Okay. All right, how about this?
Okay na po.
All right. So I just want to make it clear for the bipolar transistor. So the output current is the collector current IC, and the output voltage of the transistor is the collector to emitter voltage VCE, and the operation would be at a lower collector to emitter voltage. The collector current is proportional or linear with the collector to emitter voltage, and at some point the collector current becomes almost constant. All right, so this is the output characteristics for a bipolar transistor. And for the bipolar amplifier, this region is what we refer as the active mode of operation. So this is the region wherein the collector current is almost constant. And from this point downwards, that is what we refer as the saturation operation. All right. So again, from this point up to this point, that is referred as the saturation region for the bipolar transistor. And from this point onwards, that is what we call the active operating region. Now for the MOS transistor, here is the output characteristic curve. So we plot the output current, which is the drain current, versus the output voltage of the transistor, which is the drain source voltage. At lower value of the drain source current, the drain current is again linear or proportional until we reach a certain point wherein the drain current will become almost constant. So that point is what we refer as the saturation point. That is the VDS saturation, which is equal to VGS minus VTH. So that would be the point. So from 0 or above 0 up to this point, that is what we refer as the, for the MOS transistor, that is what we refer as the linear region or the triode region. All right, and then from the VDS saturation and onwards, so from this point onwards, that is what we refer in MOS transistor, that is what we refer as the saturation operating region. So if you look at the output characteristics, even though we are using active mode in the bipolar devices and saturation mode in the MOS devices, we are essentially pertaining to the same condition. We operate our amplifier circuit in a region wherein the output current is almost constant. So it is referred as active in bipolar circuits and saturation in MOS circuits. All right, is this clear to everybody?
Yes
Yes
po.
po.
All right, thank you. So again, let's return to our slides. All right, please confirm if you can again see the slides. Can you see the PowerPoint slides?
Yes po, sir.
All right, thank you. So continue. Let's have here examples of different bias circuits and how to analyze or what would be the guide equations. So let's have here a voltage divider bias. Again, that is defined by the voltage divider components, R1 and R2. And the voltage drop across R2 will provide the bias or voltage at the gate terminal of MOS transistor M1. Okay? So to analyze this, we have to define the transistor equations. First, we know that gate current is 0 and that drain current, we are going to use the saturation model. So 1/2 Kp W over L times the square root of BGS minus BTH, then times 1 plus lambda VDS. Then for the input, gate voltage is the voltage at node X, which is the voltage across R2. And we can apply the voltage division. So total voltage VDD multiplied by resistance of R2 divided by the total of the series components R1 and R2. Then we can also express gate voltage as if you take a voltage loop, it is equal to the VGS, voltage between gate and source, plus the voltage from the source terminal to ground. So you have VGS plus BS, wherein source voltage can be expressed as the voltage drop across RS. So VG can be expressed as VGS plus IDRS. Then at the output, we can have the equation, voltage equation at the output. So that would be VDD minus IDRD, and then minus VDS, and then minus IDRS. And we can also express the output equation as the drain voltage. So that would be the voltage from drain directly to the ground. So it would be VDD minus voltage drop across drain resistor IDRD, and then minus drain voltage. So that would be drain voltage from drain terminal to ground. And we can see that drain voltage would be equal to VDS plus IDRS. Then the source voltage again would be the ID times RS. So can you follow? Please confirm.
Yes po.
Thank you. Another example of a bias circuit for MOS transistor is the self-bias. So we can see that the gate terminal is not directly connected to the power supply, but instead, it is connected within the circuit. So the voltage or the bias circuit on the input gate will be coming from the circuit itself. So that is why we call it as the self-bias circuit. So again, to analyze, we can use the transistor equations, IG0 and the saturation current equation. Then at the input, we can have the voltage loop. That would be VDD minus You have here current times RD, and then minus voltage drop across RG, and then minus VGS, and then minus voltage drop across RS. So you can have VDD, and then minus IDRD, and then minus IGRG, gate current times RG, minus VGS, and then minus IDRS. So again, gate current is 0, so we can set IGRG equal to 0. So we can simplify the input current as VDD minus IDRD minus VGS minus IDRS. Then across the output, you can have VDD minus IDRD, and then minus VDS, and then minus IDRS. And again, you can have it in terms of the drain voltage. And drain voltage would be equal to VDS plus IDRS. And the source voltage will be equal to IDRS. So again, were you able to follow the equations?
Yes
Yes
po.
po, sir.
All right, thank you. So let's have here some sample problems. So let's say we are given with this biasing circuit with a VDD equal to 1.8 volts, a gate resistance of 50 kilo ohms, a drain resistor of 1 kilo ohm, and we have an N-channel MOS transistor M1. So the given parameters, we have the transconductance Kp equal to 500 microampere per volt squared. The threshold voltage VTH equals 0.6 volts. Lambda, or the channel length modulation parameter, equal to 0.1 per volt. And again, you have the circuit parameters VDD, RG, and RD. And we're asked to determine what is the maximum W over L width over length of transistor M1 to remain in the saturation. So when you say to remain in the saturation, we are referring to the condition wherein the VDS is equal to VGS minus VTH. All right? So we can use the drain current at saturation to determine the size, the W over L. So you have ID equal to 1/2 Kp W over L times VGS minus VTH squared times 1 plus lambda VDS. So we can compute for the W over L. But before we can solve for the W over L, we need to determine the drain current, the VGS, and the VDS. So for our VGS, we can use the voltage loop, Kirchhoff's voltage loop at the input. So that would be VDD minus IDRG and then minus VGS. So for the MOS transistor, gate current is 0. Therefore, VGS is equal to the VDD, which is 1.8 volts. Then, for the VDS, we can apply the condition to remain in saturation. So meaning that VDS is equal to the saturation point, which is VGS minus VTH. So we can subtract 1.8 volts with 0.6 volts of threshold voltage. So VDS is equal to 1.2 volts. Now for the drain current, we can use the Kirchhoff's voltage loop at the output. So you can have VDD minus IDRD and then minus VDS. So we already know the VDS, so we can solve for the drain current. So VDD minus VDS over RD, so that gives us 0.6 milliamperes. So after knowing ID, VGS, and the VDS, we can now compute for the W over L. So for this example, W over L equals 1.49. So we can use a unit of micrometer per micrometer. All right, so did you follow?
Yes po.
How about the others?
Sir, paano po ulit nakuha yung W over L, sir? Given na po ba siya?
Hindi, dito. Ipa-plug in mo na rito sa equation sa taas.
Okay po. Okay po.
Sir, dyan po ba gagamit ng parang shift solved ulit po?
Yes, oo. Kaya ako nilagay yung mga final answer para practicein nyo with your calculators o kung naman yung computer na ginagamit nyo. Okay?
Okay.
Okay po.
Sir, yung ano po, AP, ano pong parameter? Transconductance po ba?
Yung,
KP po.
eto, given naman.
Okay. Ano pong ano niya? Anong parameter niya? Yung KP?
Yung KP, it describes, ano na yan, provided na, no? It describes the characteristic of the MOS transistor on how much drain current, yun yung microampere mo, no? How much drain current will be provided for a given VGS. Kaya micrometer per volt squared. For every square of the VGS, how much will be the effect on the drain current? Yun yung ibig sabihin ng KP natin.
Okay po, thanks po.
Okay, thank you. Other clarifications? Okay, if there are none, let's proceed with the next sample problem. So we're given this time with a voltage divider circuit with VDD equal to 1.8 volts, drain resistor of 500 ohms. Then the drain current is specified to be equal to 3 milliamperes. Transistor size, W over L is 18 over 0.18. And the input resistance is said to be 30 kilo ohms. Then transistor parameter Kp is 500 microampere per volt squared. VTH or threshold voltage 0.6 volts. Channel length modulation lambda 0.1 per volt. So we're asked to determine what are the values of R1 and R2. To set the drain current equal to 3 milliamperes and to set the R in equal to 30 kilo ohms with the given W over L of 18 over 0.18. So W over L equal to, ilan to balit? 100, no? Equal to 100. Okay? So for the R1 and R2, we can use the input resistance equation. So the R in would be equal to the parallel combination of R1 and R2. So we get the product over the sum of resistances R1 and R2. So from here, we have to determine R1 and R2. All right, so you have two unknowns. R in is provided, so hindi pa natin ma-solve agad yan. No? So we'll need another equation. Let's try to form another equation for R1 and R2 using the input voltage. So gate source voltage, since the source is directly connected to ground, so BGS is the same voltage drop across R2, and it is equal to the voltage division. So you have VDD times R2 over R1 plus R2. So we combine the two equations. So you can write the two equations as VGS is equal to VDD, R2, and then we try to express R1 in terms of R in and R2. So I think yun ang nilagay natin dito, no? Or yung ano mismo yung sum, R1 plus R2. What is R1 plus R2? So lipat mo yun sa kabila. So R1 plus R2 is R1 over R2 times R in. Pwede nating ilagay rito, no? And then from there, we can cancel out R2. So we are going to reduce the unknown to R1. So you have VDD times R in over R1. that is equal to VGS. So before we can solve R1, we need to determine the value of VGS. Alright, nasundan ba? Please confirm.
Yes
So,
po.
ba't mo po nagkaroon ng R in doon, sir? Sa baba po.
Dito galing yan. So VGS is BDD times R2 over R1 plus R2. Ang nireplace natin yung R1 plus R2. R1 plus R2, ito rin yun. Cross multiply mo lang. So R1 plus R2 equals R1 times R2 over Rin. Yun yung
Okay.
pinlagay natin.
Okay po.
Alright? So ano lang to, it so happen, nakalatag na to rito sa slides, no? Pero during my analysis, normally basta maglagay ka lang ng mga equations mo, and then from there, you think of how to eliminate yung mga unknowns, di ba? Okay?
Yes po,
But
sir.
what I am showing here, yung kumbaga direct to the point, no? Pag R1 and R2 ang hinahanap, mag-form ka na agad na equation to define R1 and R2. And then from there, you will know what are the needed parameters to solve those unknowns. So in this example, nandito na tayo. To determine R1, we need to first determine the value of VGS. So as for the VGS, you can have the drain current equation. All right, so you have this equation. ID is provided, VGS is unknown, and VDS unknown din. No? Kailangan din natin yung value ng VDS. So before we can solve for the VGS, we need to determine the VDS. So we can have a voltage loop at the output. So you have VDD minus IDRD and then minus BDS. So ID is provided, RD is given, BDD is given. So we can solve for the VDS equal to 0.30. Then substitute this value dito sa drain current equation. So we can now determine the value of VGS. So you now have 2ID over KPW over L times 1 plus lambda VDS, then plus BTH. So naka-square root, no? Kasi squared yun. So use this, then we solve VGS equal to 0.94. All right, then substitute here, you can solve now for R1. Then after knowing R1, substitute this equation, you can solve for R2. All right, so were you able to follow the equations and the analysis? All right, thank you. How about the others? May clarifications ba?
Same formula rin po ba yung gagamitin to solve for R2 po, sir?
Ito yung Rin, dito na kinuha yan.
Okay po, sir.
Okay, so again, try to solve this again on your own and check whether you will arrive at the same final answers. Okay, let's move on to another example. So we're given this kind of biasing circuit. Transistor parameters, Kp is 500 microampere per volt squared. Threshold voltage VTH is 0.6 volts. Channel length modulation parameter lambda equals 0.1 per volt. And from the schematic diagram, VDD is 1.8 volts. Gate resistor is 10 kilo ohms. Drain resistor is 1K, source resistor is 100 ohms. And we're asked to determine the transconductance parameter GM without going into the triode region. So again, it means the VDS will be at the saturation point. So VDS will be equal to VGS minus VTH. So for the transconductance, this is the equation. So GM or transconductance is equal to the square root of 2 times Kp times W over L times ID. So before we can determine GM or transconductance, we need to solve for the W over L as well as for the drain current. So you have two unknowns before we can determine GM. For ID and W over L, they are defined in the drain current in the saturation model. So you have ID equal to 1/2 Kp, W over L times the squared of BGS minus BTH times the quantity of 1 plus lambda BDS. So there is ID and W over L, but we have other unknowns, more unknowns. You have BGS and VDS. So again, VGS from the drain current or from the input loop. Then as for the VDS, it would be from the output loop or using the saturation point description. So for BGS, we use KVL, Kirchhoff's voltage law at the input circuit. So that will be VDD minus IGRG minus VGS and then minus IDRS. So again, IG is 0, so we can simplify the equation to VDD minus VGS minus IDRS. So from here, we still do not know VGS and ID. While for the VDS, we can formulate the equation from the output circuit, VDD minus IDRD minus VDS and then minus IDRS. So again, you have unknowns ID and VDS. Then we can also apply the saturation condition, which says that VDS is equal to VDS sat. So without going into the triode region. So meaning the VDS is at the minimum should be at the VDS saturation, which is equal to VGS minus VTH. So you have this. So from here, so what happened here is, so from this equation, you have VDD minus IDRD and then minus VDS minus IDRS. So we substitute the value of VDD using from these three equations. So from here, VDD equals VGS plus IDRS. So that is the VDD. And then minus IDRD. And then minus VDS. So we use this description for the VDS. So VDS is VGS minus VTH. Then minus IDRS. So from here, we can simplify. BGS gets eliminated. So VGS minus BGH, minus BGS, cancelled. Then you have plus IDRS minus IDRS, cancelled. So the equation will become minus IDRD plus BTH equal to 0. So we can compute for the drain current equal to VTH divided by the drain resistor. So VTH is given, RD is given, so we can calculate for the drain current. Okay, were you able to follow? Please confirm.
Yes po.
How about the others?
Yes po, sir. No questions.
Okay
All
naman
right.
po.
So we continue. So after knowing ID, pwede na nating ibalik dito sa taas muna. After knowing ID, you can calculate for the VGS. Then after knowing VGS, you can compute for the VDS. Right? Then from there, we can compute for the W over L. Then afterwards, we can compute for GM. So VGS, you can use this equation. All right. Then after knowing VGS, you can use this to solve for the VDS. Then plug in here to determine the W over L. Then finally, knowing W over L and ID, we can calculate for GM. So for this example, GM is 997.32 microsiemens. All right. So can we continue on the next sample?
Yes po.
All right, thank you. So here is another sample problem, solved problem. So again, we have a voltage divider with a source resistor. So transistor parameters of M1, Kp, VTH, and lambda are all provided. Circuit parameters, we have VDD, RD, RS, and source voltage is given. So Vs is 250 millivolts. So we're asked to determine what is the minimum W over L to maintain saturation. So again, the description to maintain saturation would give us the equation VDS must be equal to the VDS saturation equal to VGS minus VTH. All right, so for the W over L, we can find it from the drain current equation. So before we can solve for the W over L, we need to know ID, VGS, and VDS. So for the ID, we can use the voltage drop across the resistor RS. So Vs is given. So Vs equals IDRS. So since Vs is provided, Rs is provided, we can calculate for ID. Right? Then, for the VDS, we can use the output loop. So you have VDD minus IDRD minus VDS and then minus IDRS. So from there, we can compute for the VDS equal to 0.3 volts. Then for the VGS, we use the saturation condition. Is equal to VDS sat equal to VGS minus VTH. So we can solve for the VGS. So after solving ID, VGS, and VDS, we can now calculate for the W over L. So just plug in the parameters. So W over L is 107.87. All right, so is the example clear?
Sir,
Opo.
yung sa ano po, yung equation po dyan, tapos yung sa shift solve po, parehas lang po ba yung kalalabasan?
Dapat, yes.
Yung parehas lang din po ba pag maximum po yung hinahanap sa W over L po?
Yung maximum, walang ano yon, walang limit yon. So, kasi yung ID kasi saturation point ang pinag-uusapan, no? So for the saturation point, we are referring to the minimum value of ID.
Okay po, sir. Thank you.
Then nahirapan na mag-control nung Zoom eh. So from the, imaginein muli yung ano natin, yung ID versus VDS. So the transition from the triode and the saturation is the saturation point. So ang trend nun from linear or triode, drain current is increasing. Right? And then at the saturation point, you start with the saturation region. So the saturation point indicates the minimum drain current. Pag mas bumaba ka ba doon, lalabas ka na, mapupunta ka na sa linear region. So since we are referring to the minimum drain current, and from the equation, yung W over L, proportional siya dun sa ID, directly related. So if you are finding the minimum ID, you also need the minimum W over L. So hindi ipapahanap sa atin yung maximum.
Okay po, sir. Thank you po.
Okay, thank you. Alright, sandali, naghang ako. Alright. Ano yung tsura ng slide sa side nyo?
Yung sample 4 po, sir.
May kulay itim ba? Wala.
Wala naman po.
Okay, sa akin merong nakaharang yung mga controls. Give me a minute. Right, naghang ako. Pag nilabas yung ano eh, naghahang. Right. Alright, so can you see yung slides again?
Sample problem, sir.
Okay. So let's continue on the one more example. So we are given this circuit. So again, KP, VTH, and lambda are provided. So whenever we have a three-terminal symbol, it is assumed that the bulk and source are shorted or connected together. So VSB is assumed to be 0, and therefore the VTH will be equal to the VTO. So that is why we don't need to calculate for the VTH. No? So given na agad siya. Okay? And then for the circuit parameters, VDD is provided. Drain resistor is 500 ohms. Source resistor is 200 ohms. And then we're asked to find the value of resistors R1 and R2. With the transistor size, the value 18 micrometers, length is 0.18 micrometers, and the drain current equal to 1.2 milliamperes, and the current along R2 is given as 0.1 milliamperes. So before we can solve this, you have to define the current. So current, excuse me, flowing through R2 is the IR2. Current flowing through 500 ohms is drain current. Then that drain current will also be the same with the source current. However, at this point or along RS, the current will now be ID plus IR2. All right, is this clear?
Yes po.
All right. Then as for resistor R1, the current is also IR2. You have the same current flowing through R1 and R2, and that is because gate current is 0. So all of the current flowing here is all coming from R1. Right? So these are the current indications in the circuit. So for resistor R2, we can use the gate source voltage. So R2 is connected from gate to source. So VGS is equal to IR2 times R2. So we can solve R2 by knowing the VGS. So for the VGS, we can use the drain current equation. But before we can solve for the VGS, we have to know the value of VDS. Other parameters are given. So for the VDS, we can use voltage loop at the output. So VDD minus IDRD minus BDS minus ID plus R2RS. So all parameters are provided, so we can solve for the VDS equal to 0.936 volts. Substitute it back to this equation, we can solve for the VGS. And after knowing the VGS, we can solve for the resistance R2. Okay, can you follow?
Opo.
Thank you. And then for R1, we can do a voltage loop at the input. So you have VDD minus IR2 R1 minus IR2 R2 and then minus ID plus R2 RS. So the only unknown parameter is R1. So we should be able to solve it. Equal to 6.05 kilo ohms. All right, is this clear?
Yes
Sir?
po.
Yes,
Bakit
clarification, question.
Bakit po ulit nagiging 0 yung IG?
Because of the structure of MOS transistor, the between gate, drain and the drain and source, you have the insulating oxide layer. So meron siya ritong oxide, which is a electrical insulator.
So, bali sir, always pong IG is equals to 0 po.
Correct, correct. And even in the schematic symbol, we can see that you have an open circuit. Di ba? So wala siyang continuity or connection between gate and the drain and source. So IG will always be 0. Correct.
Okay po sir. Sir, sa VTH po, paano po ulit naging ano siya? 0.6 po ulit.
Given na yan, given.
Yung na-explain niyo po kanina sir, yung nag-equal po siya.
In case we have the BSB, okay, naka-share screen pa ako. All right, so can you see the slides?
Yes po sir.
All right, so in case BSB is given, ito yung parameter na to. In case the BSB is given, you have to calculate the VTH. Okay, kung sakaling given yung BSB. But for this symbol, the bulk terminal is not indicated. So we are going to assume that the bulk is shorted or connected internally with the source. So we are going to assume that BSB equals 0. Yun ang assumption natin dito. So this becomes square root of P minus square root of P. Therefore, the VTH will be equal to the VTO. So dun sa mga given sa assumption natin doon, yung 0.6 volts, that is the same as the VTO. That is the threshold voltage when the VSB is equal to 0. Nakuha ba yon?
Okay po sir, thank you po.
Okay. So that ends our example for the analysis of the bias circuits.